All right, we're starting chapter 4 about probability, and the first lesson is about randomness, probability, and simulation. Chance is all around us. The mathematics of chance behavior is called probability. Chance behavior is unpredictable in the short run, but has a regular and predictable pattern in the long run. The probability of any outcome of a chance process is a number between 0 and 1 that describes the proportion of times the outcome would occur in a very large number of repetitions. Okay? That's true definition of probability. Outcomes that never occur have a probability of 0. An outcome that happens on every single repetition has a probability of 1. An outcome that happens half the time in a very long series of trials has a probability of 0.5. The fact that the proportion of heads in many tosses of a coin eventually closes in on 0.5 is guaranteed by the law of large numbers. The law of large numbers says that if we observe more and more repetitions of any chance process, the proportion of times that a specific outcome occurs approaches its probability. Okay? You could flip a coin 10 times and get 6 heads and 4 tails. That's not 50%, but if you did that like 100 or 1,000 times, you would find out that the probability would come closer and closer and closer to 0.5, like it's supposed to, because you need a large number of repetitions. Now, we can model chance behavior and estimate probabilities using a simulation. A simulation is the imitation of chance behavior based on a model that accurately reflects the situation. So how do you do a simulation? Well, you have to ask a question about some process, describe how to use a chance device to imitate one repetition of the process, and tell what it is you're going to record at the end of each repetition. Perform many calculations or repetitions, and then last, use the results of your simulation to help you answer the question. And you're going to see some of that in this chapter. All right, so first example. Suppose a married man and woman both carry a gene for cystic fibrosis, but don't have the disease themselves. According to the law of genetics, the probability that a child will develop cystic fibrosis is 0.25. Explain what this probability means. If the couple has 4 children, is one of them guaranteed to get cystic fibrosis? Explain that. Okay, so remember, it's over the long run that these probabilities have been found to be true. So when you explain what a probability means, you always have to say if you take a very large random sample of whatever. So we'll start there. Random sample of children. Parents carry the gene for cystic fibrosis, but don't have the disease themselves. About 25% of the time, about 25% of the children will develop CF. Okay, so that answers what probability means. Okay, take a very large sample of children whose parents carry the gene but don't have it. About 25% of those children will develop CF. Now, second part. If the couple has 4 children, is one of them guaranteed to get cystic fibrosis? Guaranteed is the key word here. Okay, you would say no, there's no guarantee here. Probability describes what happens in many repetitions. Okay, it's just what happens in many repetitions. It is not a guarantee. Right? A lot of thinking, a lot of wording. Good example 2. Pedro drives the same route to work on Monday through Friday. His route includes 1 traffic light. According to the local traffic department, there's a 55% chance that the light will be red. Explain what this probability means. Right, remember, if you take a very large sample, it's always your first part. Let's do this. If you take a very large sample, large random sample, times during the day, and record the color of the traffic light, about 55% of the time, light will be red. Okay? But it always starts with you have a very large random sample of blank, whatever it is in the context of the problem. Anytime it asks you to explain what that probability means. All right, example 3. Imagine tossing a coin 6 times and recording the heads or tails of each toss. Which of the following outcomes is more likely? Heads, tails, heads, tails, tails, heads, or tails, 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 heads, heads, heads? Justify your answer. Well, probability of a head, when you flip a coin, is 1/2. Probability of a tail is 1/2, or 0.5, right? So the probability of each outcome is exactly the same, and you're just doing it 6 times. Okay? So the probabilities are the same. Since the probabilities of each outcome is the same, the probability of doing it 6 times in a row is still the same. All right? So we would say the two sequences are equally likely. Any specific sequence of 6 coins has a 1/2 to the 6th power, which is going to be 1/64, probability of a. Alright, and this is true, like I said, because the probability of getting a heads is the same as probability of getting a tail. So any order of heads and tails, if you do it 6 times, is going to have the same probability. Okay? Number 4. Basketball announcer suggests that a certain player is streaky. That is, the announcer believes that if the player makes a shot, the player is more likely to make the next shot. As evidence, the announcer points to a recent game where the player took 30 shots and had a streak of 10 shots made in a row. Is this convincing evidence of a streaky shooting by the player? Assume that this player makes 50% of the shots and that the results of the shot do not depend on previous shots. Okay? So describe how you would carry out a simulation to estimate the probability that a 50% shooter who makes 30 shots in a game would have a streak of 10 or more shots. Okay? Do not perform the simulation. So it's saying set up something to be able to repeat this process over and over and over. Okay? To see how often does it happen that you would get 10 or more shots in a row. So this is kind of like our random assignment steps. So let me show you how to do this. First, you would say let 1 equal you make the shot, and 2 equal the missed shot. All right. Then I would say use that random integer, and you can say choose between 1 and 2, taking a random sample of 30 shots. If we put this 30 there, it's going to repeat the process 30 times. So you have a string of 1s and 2s, okay? And it's going to simulate taking the random sample of 30 shots. And then what do? You would record the longest streak of made shots in the sample. Remember, made shots was 1s. Okay? So this will give us an idea of how often does it happen that you could get 10 in a row, right? 50-50 shots, so 1 and 2 are our 2 outcomes. Now, same problem. Part B says the dot plot displays the results of 50 simulated games in which the player took 30 shots. What conclusion can you draw about whether this player was streaky? Well, we said they made 10 shots in a row, right? How often did that happen? Well, it only happened 1 time in the 50 simulated games. So 1 out of 50 is 0.02. All right? So what would we say about this? We would say assuming player makes 50% of his shot and the result of 1 shot does not affect does not depend on the previous shot. The estimated probability that a player would have a streak of 10 or more is 0.02. Remember, we calculated that up there. And what does that tell us? This is convincing evidence that the player is streaky. Remember, if it's less than 5%, we consider it convincing evidence of whatever the outcome is. In this case, that the player is streaky. Okay? So, this is our introduction to probability, and a lot of this lesson is just interpreting what does probability mean. How can we recreate a situation to see how often something really happens? Okay? So hang in there, and we'll get started.